Have a look at this molecule, 2,4,5-trimethoxybenzaldehyde. It's a research chemical that's pretty hard to make from scratch. If you want to prepare a molecule like this, it's usually best to start from a more widely available molecule that has most of the structural features already in place. The most similar molecule that's readily available is vanillin, which has 2 of the 3 oxygens already on the ring, but the biggest challenge there is selectively getting a substituent onto the 2 position instead of the 3 or the 6. Although the 4-hydroxy group activates the 3 position, the 5-methoxy group also activates the 2 and 6 positions, meaning that any kind of substitution reaction on the ring would result in a mess of 3 different isomers, 2 of which would be unwanted. There is, however, a molecule that occurs in nature that already has a 2,4,5-trimethoxybenzene ring. This molecule is asarone, the major component in the essential oil of A.k.a. calamus. This plant, known among many other names as the sweet flag, the calamus root or the muskrat root, grows in Asia, Europe and North America, and the percentage of asarone is highest in the Indian variants. Asarone exists in 3 different isomers, alpha, beta and gamma, depending on the position and orientation of the double bond. The main one found in calamus oil is beta-asarone, which has the double bond next to the ring in a cis orientation. Incidentally, the name asarone is misleading as it implies the molecule has a ketone group, but it doesn't. Although the alpha isomer has some medicinal benefits, the beta isomer is actually pretty nasty stuff, being a suspected human carcinogen. There are several ways to isolate asarone from calamus oil. The most common method is high temperature vacuum distillation, but calamus oil is not cheap or easy to find. My apparatus is too big to deal with such small quantities of material, and I don't have enough confidence to heat my glassware to nearly 200 degrees under vacuum. I've done this once before, and although the apparatus didn't implode, the round bottom flask containing the distillant got a nice new concave base like a fancy wine bottle. In fairness, this was due to me heating it pretty aggressively. Another method is to isomerize beta-asarone to alpha-asarone, which is a crystalline solid, and separate it from the rest of the oil, which also contains terpenes, fatty acids and other unwanted compounds. Olefins next to aromatic systems can be isomerized with catalytic amounts of iodine in the presence of heat or UV lights, and the reaction is faster with electron-rich aromatic systems. Since the alpha and beta isomers of asarone both contain 3 methoxy groups, they have very electron-rich aromatic systems, making this a viable method. The reagents used were calamus oil, 10 grams, ethyl acetate, 40 ml, iodine, a tiny unmeasurable trace, sodium thiosulfate, 2 grams, sodium hydroxide, 4 grams, deionized water, 60 grams, sodium sulfate, heptane, 25 grams, and methanol, 20 grams. Ethyl acetate was weighed into a round-bottom flask. Calamus oil and iodine were dissolved in it, then the mixture was refluxed for an hour and a half. As the mixture was cooling, sodium thiosulfate was made up to 10% with water, and sodium hydroxide was also made up to 10% with water. Once it was cooled, the mixture was washed with the sodium thiosulfate solution to neutralise the iodine, and then with the sodium hydroxide solution to remove any fatty acids or molecules with phenol groups. Given that the caustic soda solution turned orange and a pasty soap-like precipitate formed in it soon after, it seems that these materials formed a significant part of the oil. The now turbid reaction mixture was filtered by vacuum, dried with sodium sulfate, then filtered again by gravity. Gravity filtration was slowed down by formation of a white crystalline precipitate, which may well have been the desired product. This also appeared on the filter paper once the sodium sulfate had been discarded and it had dried out. This had not happened in previous runs where I'd used less caustic soda. Once washed, the solvent was removed from the vacuum mixture by vacuum distillation to limit decomposition and allow as much of the solvent to be boiled off as possible. It yielded a viscous oily liquid with suspended particles in it, again different to earlier runs which had just produced viscous oil. This mixture was suspended in heptane, heated to boiling, then filtered by gravity to remove any insoluble material. The insoluble material in question was some brown gunk that stuck to the flask. Once filtered, the filtrate was reheated to 80 degrees, boiled down to about half its initial volume, then cooled to room temperature with stirring, where it became a viscous clear liquid. It was then cooled in the fridge overnight. The reason for the stirring during cool down is that all forms of asarone have melting points below the boiling point of heptane, and I found that alpha-asarone tends to form supersaturated solutions. Its apparent failure to precipitate was a major cause of poor yields and general frustration in my earlier attempts to isolate it. Cooling in the fridge caused solid material to form. Methanol was added to the mixture, causing more white solids to appear. The mixture was heated to boiling, the volume was reduced to around 20 ml, and the mixture was cooled to room temperature with stirring, with the thermometer placed in the beaker to generate turbulence, help with nucleation, and help the solution break free from the tyranny of supersaturation. Around 45 degrees, fine off-white solids formed in the mixture, and within seconds a substantial amount of product precipitated out. It was cooled in the fridge overnight. The mixture was placed on the pump, but there was so little liquid left that nothing came through. It was washed dropwise with methanol to remove entrained liquid, and dried on the pump for a further 15 minutes. The final product, alpha-asarone, was isolated as a white powder with a melting point of 62 to 66 degrees, with a balsamic, slightly woody smell similar to that of calamus oil itself. The yield was 5.2 grams. This is an efficient, if slightly laborious method of producing high-purity alpha-asarone. Without knowing how much beta-asarone there was in the starting material, I can't give an exact figure of how efficient it is. As pure beta-asarone solidifies around 15 to 20 degrees, and my calamus oil stayed liquid at 4 degrees, it's fair to say it contained a significant amount of non-asarone material. The way the reaction works is this. At high temperatures, iodine molecules split into iodine radicals, the most obvious sign being the fact the orange colour characteristic of iodine fades as the mixture heats up. An iodine radical attacks a double bond of the asarone molecule, forming a carbon-centred radical. As carbon is a much smaller, less polarisable atom than iodine, this radical is less stable than the iodine radical, and it mostly reverts back to the starting material, reforming the double bond. However, the more thermodynamically favoured double bond, the trans bond, is formed by preference. The more electron-rich the aromatic system is, the more reactive the double bond is to electrophiles like radicals, and the faster the reaction is. As the cis and trans isomers are in equilibrium, 100% conversion is generally not achievable, but it does ensure that the trans isomer is the major product. I have tried longer reaction times in previous runs, and these do not result in greater yields. The reaction can be carried out with catalytic quantities of iodine, as in less than 1 mol%, so any addition products are kept to a minimum. After that, extracting the asarone from the mixture is a process of elimination, first removing the iodine from the mixture with sodium thiosulfate, then the phenols and fatty acids with sodium hydroxide. Asarone is insoluble in heptane at room temperature but dissolves at high temperatures. Anything insoluble in hot heptane is not the desired product, so it can be removed by filtration. In a similar way, it's insoluble in methanol at low temperatures due to its low dipole moment, and anything remaining that is soluble in methanol can be removed by filtration. The fairly sharp melting point indicates any impurities present are insignificant. All in all, this is a reasonably efficient and quite enjoyable way to extract a white powder from a yellow liquid. In the near future, I can hopefully demonstrate a way to convert asarone into the benzaldehyde shown at the start. I hope you enjoyed this video. Thank you for watching.